systems of equations in 3 variables. So, when we have a system of equations in 2 variables, we get, oh boy, that's not what it meant to do. When we have a system of equations in 2 variables, we get 2 lines. So we have a line like this and a line like this, and they intersect at a point. When we have 3 variables, instead of lines, we have planes. And so if there is one solution, then we have 3 planes that intersect at a point. If our 3 planes intersect in a line, then we get our infinitely many solutions. If our 3 planes don't intersect, then we get no solution. So here, 2 of the planes intersect, and 2 of the planes intersect, but the blue and the green one are parallel. Or here, each pair of planes intersects, but they don't all intersect, or here where they're all parallel. Don't worry, I am not going to make you graph things in 3 dimensions, because graphing things in 3 dimensions sucks. We're not doing that. We are just going to solve these algebraically. Solve the system of equations by elimination. So, the same thing that we did with our previous, when we solved systems with 2 equations by elimination, we can also solve systems of 3 equations by elimination, and it works basically just the same. So we want to get rid of one of our variables. So looking at these variables, the x's, the y's, and the z's, I have a positive 1z and a negative 3z and a negative 5z, and so that seems like that's going to be the easiest to eliminate. So we're going to use this first equation to eliminate the z's in the second equation and the z's in the third equation, and then that gives us 2 equations with 2 variables, and then we can solve those, and then we can work backwards until we solve for all of them. It works basically the same as solving for 2 variables, except we have to do the steps a bunch more times. So we'll start with these first 2 equations. So we have x minus 2y plus z equals 15, and 2x plus 3y minus 3z equals 1. And we're going to multiply this whole first equation by 3 in order to cancel the z's out. So we're going to make this be 3x minus 6y plus 3z equals 45. And we're going to add those together. And so that's 5x minus 3y, z's cancel out, equals 46. Can't do anything with that yet. Now, we're going to take the first equation and the third equation and cancel the z's out again. So we have x minus 2y plus z equals 15, and 4x plus 10y minus 5z equals negative 3. So we want to cancel the z's out, so this time we're going to multiply this one by 5. So that's going to be 5x minus 10y plus 5z equals 75. I can do basic multiplication. 75. And now we add these together, and we get 9x. This works out really nicely because our plus 10y and our minus 10y also cancel out. And our plus 5z and our minus 5z also cancel out. And then this is equal to 72, and we divide both sides by 9, and we get that x is equal to 8. Does not always happen this way. We got lucky that these y's canceled out as well. If they didn't, we would have two equations of x and y, which we would solve like a normal system of equations, and then plug back in. But here we got lucky, the y's canceled out, now we solve for x, plug this back into the equation to solve for y. So 5 times 8 minus 3y equals 46. It's 40 minus 3y equals 46. Negative 3y equals 6, y equals negative 2. And now we take both of these and we plug these back into one of our original equations, doesn't matter which, I'm going with the first one, in order to solve for z. So 8 minus 2 times negative 2 plus z equals 15. That's 8 plus 4 plus z, which is 12, plus z equals 15, which means that z equals 3. So our answer is 8, negative 2, 3. And so we're going to write that as an ordered triple, which is like an ordered pair, except you have 3 of them. So use elimination to eliminate one variable from 2 equations, and then solve those 2 equations like normal, and then plug those back in to solve for the third variable. It's just the same, except it takes a lot more time. And we can also do this by substitution, if we can get one variable by itself. So 3x equals 9y, very easy to divide that by 3 and make that x equals 3y. Now we can plug that back in to both of the other equations, and that will give us a set of equations of y and z that we can solve. So this is 3y minus 2y plus z equals 7. And we're going to combine our like terms here and make this y plus z equals 7. Negative 3 times 3y plus 4y plus 2z equals 0, which is negative 9y plus 4y plus 2z, which is negative 5y plus 2z equals 0. This, we can then solve for one of our variables. I'll subtract z from both sides and make this y equals negative z plus 7. And then plug that in here to solve for z. So negative 5 times negative z plus 7 plus 2z equals 0. That's going to be 5z minus 35 plus 2z equals 0. We'll add the 35 to both sides and combine our like terms. So we get 7z equals 35, which means that z equals 5. Now take that, plug that in to solve for y. So y equals negative 5 plus 7, which is 2. Take that, and oh, actually, because we had already solved for x in terms of y, so take the y and plug back in here. We could plug the y and the z into one of these, but that's more work. So x equals 3y, which is 3 times 2, which is 6. So our ordered triple is 6, 2, 5. In 1998, Cynthia Cooper of the WNBA Houston Comets basketball team was named Team Sportswoman of the Year by the Women's Sports Foundation. Cooper scored 680 points in the 1998 season by hitting 413 of her 1-point, 2-point, and 3-point attempts. She made 40% of her 160 3-point field goal attempts. How many 1, 2, and 3-point baskets did Miss Cooper complete? So, in order to solve for three different variables. So 1, 2, and 3. We'll say that 1 point is x, and 2 points is y, and 3 points is z. We need three different equations here. So she scored 680 points in the season. So 1 point for every x, plus 2 points for every y, plus 3 points for every z gets her 680 points. She hit 14 of her points. So x plus y plus z equals 413. She made 40% of her 160 3-point field goal attempts. So 160 times 40% is 64. So that tells us that the number of 3-pointers that she made was 64. Because we have z by itself, that makes substitution seem like a good choice here. So we're going to take this z and plug this into the other two equations. So x plus 2y plus 64 times 3, which is 192, equals 680. And x plus y plus 64 equals 413. And so x plus 2y equals 488. And x plus y equals 349. Now, here, again, you can do substitution or you can do elimination. Doesn't matter. I'm going to do elimination now. We can mix and match, right? We did substitution here, but now we can do elimination. So I'm going to make this subtract x, so minus x plus y equals 349. And so x minus x, the x's go away. 2y minus y is y. 488 minus 349 is 139. Here, the 1, 3, yeah. So y is 139, and we know that x plus y is 349. So x plus 139 equals 349. And so minus 139 from both sides, that is 210. And so double check. It's 139 plus 64 is 413. Yeah. So there's my x. So I have 210 1-point baskets, whatever team we're playing, and 139 2-pointers and 64 3-pointers. And so what I did to check was take the x, the y, and the z and plug them into this second equation to make sure that they added up to 413 and that I didn't mess up my arithmetic somewhere. Technically, I should also plug them back into the first one to double check, but I'm going to trust my math here. And that's it for 2.2, short and sweet. Very, very similar to 2.1, solving the system of equations. It's just more work because you got more steps. So thanks for joining me. Turn in next time for 2.3, modeling real-world data with matrices.